Welcome to the deep dive. Today we're climbing into the cockpit, so to speak. We're doing an in-depth look at aircraft flight instruments.
That's right.
You've shared some great material, excerpts from the Pilot's Handbook of Aeronautical Knowledge, Chapter 8 specifically.
Yep, Chapter 8's a solid source.
And our mission here is really to pull out the most important stuff. You know, how these instruments work, what errors can pop up, and why knowing all this is just crucial for safe flying.
Absolutely crucial. And that chapter gives us a fantastic starting point. We'll be digging into the systems behind these gauges, the pitot-static system, gyroscopic principles, which are fascinating, and even the good old magnetic compass. We'll see how they turn, well, forces like air pressure and motion into the numbers pilots rely on constantly.
Right.
Getting a handle on how they work, that's the first step to really trusting your instruments, but also knowing when maybe they're leading you astray a bit.
Okay, so kicking things off then. The pitot-static system, you said it combines different air pressures. Tell us the basic idea.
You got it. It's quite ingenious, really. The pitot-static system uses static pressure that's just the ambient air pressure around the plane.
Okay, like the air pressure right here, right now.
Exactly. And it combines that with dynamic pressure. That's the extra pressure created by the aircraft actually moving through the air.
So the pressure you feel when you stick your hand out of a moving car window, that kind of thing.
That's a great analogy, yeah. That feeling of force, that's dynamic pressure.
And this combination of pressures feeds some key instruments.
Precisely. The big three that rely on this system are the airspeed indicator, or ASI, the altimeter, and the vertical speed indicator, the VSI. The Handbook's figure 8.1 shows how they're all linked up.
Okay, let's start with the pitot tube, that little tube sticking out the front, right? What's it measuring?
That's the one. The pitot tube measures total pressure. And total pressure is simply the sum of that static pressure plus the dynamic pressure.
So static pressure is always there, whether you're moving or not.
Correct. It's just the local atmospheric pressure.
And dynamic pressure only happens when there's movement relative to the air.
Exactly. And interestingly, the Handbook points out it doesn't matter if the plane's moving through still air or if it's flying into a headwind. If the relative speed is the same, the dynamic pressure is the same. Wind itself creates dynamic pressure against the aircraft.
Interesting. And the tube itself, it has specific openings.
It does. There's the main opening right at the front, facing forward, that collects the total pressure. And then there's usually a small drain hole, often on the back or bottom.
What's the drain hole for?
That's to let any moisture out rain. Cloud droplets, condensation. It needs to drain so it doesn't freeze or block the tube.
Okay.
And checking those openings during pre-flight is absolutely critical.
Yeah.
You know, bugs love making nests in there.
Seriously?
Oh, yeah. Or just forgetting to take off the pitot tube cover. If either opening is blocked, your airspeed reading is going to be wrong. Simple as that.
Right. Speaking of airspeed, how does the ASI use that total pressure and the static pressure to give us a speed?
Okay, so the ASI gets the total pressure feed from the pitot tube, but it also gets a separate feed of just static pressure from the static port.
Okay.
Inside the instrument, there's a diaphragm. Total pressure goes into the diaphragm. Static pressure surrounds it in the instrument case. The instrument mechanically subtracts the static pressure for the total pressure.
Leaving just the dynamic pressure.
Exactly. And that dynamic pressure is directly related to airspeed. So the diaphragm expands or contracts based on dynamic pressure, and that moves the needle on the ASI. More dynamic pressure, higher indicated airspeed.
Clever. Now, you mentioned the static port. That seems pretty important, too, since it feeds multiple instruments.
It is. The static port, sometimes there are two, one on each side of the fuselage, is positioned very carefully. It needs to be in a spot where the airflow is as undisturbed as possible to get a really accurate sense of the ambient atmospheric pressure.
And that pressure goes through lines to the ASI, altimeter, and VSI.
Correct. It provides the static reference for all three.
Okay, the handbook also talks about an alternate static source located inside the flight deck. When would you use that?
That's your backup. Imagine your primary static port gets blocked, maybe by ice.
Right.
Suddenly your altimeter freezes, your VSI reads 0, and your ASI becomes unreliable. Not good. So some planes have an alternate static source selector. Flipping that switch tells the instruments to start using the air pressure from inside the cabin instead.
But the pressure inside the cabin isn't exactly the same as outside, is it?
You're right, it usually isn't. Because of the airflow around the fuselage, the cabin pressure is typically a tiny bit lower than the true outside static pressure.
So what does that do to the instruments?
Well, because the reference pressure is slightly lower, the altimeter will read a bit higher than your actual altitude. The ASI will indicate a slightly higher airspeed, And the VSI will show a momentary climb before it settles.
Ah, okay.
The exact errors depend on the aircraft, which is why you must consult the AFM or POH. It'll tell you the corrections needed when using the alternate source.
AFM POH, Airplane Flight Manual, or Pilot's Operating Handbook.
Got it. The aircraft's Bible.
And, wow, the handbook even mentions breaking the VSI glass if the static port is blocked and there's no alternate source. That sounds pretty extreme.
It is extreme. It's definitely a last resort. But think about it. If your static source is totally blocked, you've lost reliable altitude and airspeed. The VSI, while useful, is generally considered the least critical of the three for immediate survival.
So breaking the glass basically vents the static system to cabin pressure.
Exactly. It's a desperate measure to get some kind of usable static pressure reference back to the altimeter and ASI, even if it's not perfectly accurate. It's better than nothing in an emergency.
Okay, that makes sense in a dire situation. Let's move to the altimeter. Tells us our height. The handbook calls it vital.
Understatement. It's your primary tool for knowing your vertical position. Inside, its heart is a stack of sealed metal capsules. They're called aneroid wafers.
Aneroid wafers. Okay.
They're mostly evacuated, meaning most of the air has been removed, and they're sealed with a specific internal pressure, usually equivalent to 29.92 inches of mercury.
Which is standard sea level pressure, right?
Exactly. We'll come back to that. Now, these wafers are really sensitive to outside pressure changes.
How do they react when you climb or descend?
Well, remember, static pressure decreases as you climb. So as the outside pressure drops, the higher pressure sealed inside the wafers makes them expand.
Okay.
And when you descend, the outside static pressure increases, squeezing the wafers and making them contract.
And this tiny expansion and contraction moves the needles.
Precisely. There's a complex set of gears and levers that magnify this movement and translate it into the altitude reading in feet on the altimeter face. The static pressure from the static port feeds into the airtight instrument case surrounding these wafers.
So fundamentally, the altimeter is just a very sensitive barometer calibrated to show feet instead of pressure units.
That's a perfect way to describe it, an aneroid barometer. But here's the catch. That indicated altitude is only truly accurate, spot-on accurate, under standard atmospheric conditions.
Which are?
29.92 inches of mercury pressure at sea level and a temperature of plus 15 degrees Celsius at sea level, with a standard decrease in both pressure and temperature as you go up.
And how often are conditions perfectly standard?
Almost never, which is why we have the Kollsman window.
Ah, that little window with the pressure setting.
Exactly. You use the knob next to it to dial in the current local altimeter setting. That setting is the local station pressure corrected down to sea level. By setting that, you're telling the altimeter, okay, this is what sea level pressure is right here, right now.
And that gives you a much more accurate altitude reading above sea level.
A much better approximation of your altitude above mean sea level,
Right.
MSL, yes. Still not perfect, but much closer.
Okay, and the handbook has that catchy phrase, going from a high to a low, look out below. Explain that one.
It's a classic and critical. It refers to flying from an area of high barometric pressure into an area of lower barometric pressure without resetting your altimeter.
What happens?
If you don't update the Kollsman window, your altimeter still thinks it's in the higher pressure air. Since pressure is naturally lower at higher altitudes, the altimeter's fooled into thinking it's higher up than it actually is.
Oh, it reads high.
It reads high, meaning your true altitude, your actual height above sea level, is lower than indicated. Hence, high to low, look out below. You're lower than you think.
And the opposite is true, too. Low to high without resetting means you're higher than indicated.
Correct. Less immediately dangerous, maybe, but still wrong and potentially problematic for air traffic control separation.
So getting updated altimeter settings en route from ATC or weather broadcasts like Always Sassos or Elitos is absolutely vital.
Non-negotiable for safe flight, especially IFR or near terrain. The handbook also notes some older altimeters can't be set above 31.00 inches of mercury. If the pressure is higher than that, you'll actually be higher than indicated. And flying when pressure's below 28.00 Hg might not be possible if your altimeter can't be set that low.
And it's not just pressure, right? Temperature messes with the altimeter, too.
Big time. This is a really important one. Cold air is denser than warm air.
Right.
So if you're flying in air that's colder than the standard temperature for your altitude, that denser air column below you exerts more pressure than standard air would at that same true altitude.
So the altimeter thinks you're lower down in the atmosphere than you are.
It thinks the pressure corresponds to a higher altitude than you're actually at. It reads high again.
Ah, so you're lower than your indicated altitude.
Exactly. which leads to the other rhyme. From hot to cold, look out below.
Because flying into colder air makes your true altitude lower than indicated.
Precisely. And conversely, flying in warmer than standard air means your true altitude is higher than indicated. And critically, adjusting the Colesman window for pressure does not fix this temperature error. The Handbook's figures 8.3 and 8.4 show just how significant these temperature errors can be.
Wow. So, setting the altimeter. Walk us through that process before a flight.
Okay. You find the Colesman window and the adjustment knob. You get the current altimeter setting from the local source, ATIS, ATOS, ATC.
Yeah.
You dial that number into the window.
And then?
Then, the crucial check. Compare the altitude now showing on your altimeter with the published field elevation of the airport. It should be close. The rule of thumb is within 75 feet.
If it's off by more than 75 feet.
The instrument needs checking. It's considered unreliable for IFR flight and should be inspected. And remember, that setting you get is the station pressure corrected to sea level, so it's most accurate right near the station. You'll need updates as you fly.
And even with the right setting, there can still be issues, especially higher up or in mountains.
Yes. While setting the current pressure helps everyone maintain separation relative to each other, it doesn't guarantee perfect true altitude, especially with non-standard temperatures aloft. And the Handbook specifically warns about mountainous terrain, where certain atmospheric conditions can cause the altimeter to read significantly higher than your actual altitude above sea level. Always maintain vigilance.
The Handbook example flight from Dallas to Abilene really drives home the need to update settings. A small pressure difference makes a big altitude difference.
It does. That rule of thumb again. 1 inch of mercury difference is roughly 1,000 feet of altitude error. Forgetting to update the setting from, say, 30.12 in Dallas to 29.82 in Mineral Wells means you could be 300 feet lower than you think you're passing Mineral Wells.
Yikes.
And remember, the needles move for 2 reasons. Actual altitude changes, and you physically changing the setting in the Colesman window. Even a Park Plains altimeter will change overnight if the barometric pressure changes.
Bottom line, pilot's responsibility for terrain clearance, especially in poor visibility.
Always. And follow ATC altitude assignments.
Okay, let's clarify those 5 types of altitude. It can be a bit confusing. Indicated, true, absolute, pressure, density.
Let's break them down. Indicated altitude. Simple. It's what you read directly on the altimeter when the current local setting is in the Colesman window. Uncorrected.
Okay.
True altitude. This is your actual height above mean sea level, MSL. Think of it as your chart altitude. Terrain elevations, obstacle heights on charts are in true altitude.
Got it.
Absolute altitude. Your height above the ground directly beneath you. Above ground level, or AGL. This changes constantly as the terrain below you changes.
Like what a radar altimeter would show.
Exactly. Then pressure altitude. This is the altitude shown on your altimeter when you set the Colesman window to the standard pressure, 29.92 inches of mercury. It's your height above the standard datum plane. We use it for performance calculations. And
density altitude.
Right. Density altitude is pressure altitude corrected for non-standard temperature. This is huge GE for aircraft performance.
Why is it so critical?
Because density altitude represents the effective altitude at which the aircraft feels like it's flying, aerodynamically speaking. Hot air is less dense, humid air is less dense. High density altitude means the air is thin.
So the engine produces less power, the wings produce less lift.
Precisely. Takeoff rolls are longer, climb rates are worse. It feels like you're trying to fly at a much higher altitude than the pressure altitude alone would suggest. A hot, high elevation airport on a summer day can have a dangerously high density altitude.
So calculating density altitude before takeoff, especially in those conditions, is vital.
Absolutely. And just to recap the pre-flight check, set current altimeter setting, check indication is within 75 feet of field elevation.
Perfect. Okay, switching gears. The vertical speed indicator, or VSI, tells us if we're climbing or descending and how fast.
That's its job, yeah. Also called a VVI, sometimes vertical velocity indicator, shows rate of climb or descent in feet per minute, usually. Should read 0 in steady, level flight.
How does it work? It uses static pressure too, right?
It does, but in a different way than the altimeter. It's a differential pressure instrument. Inside, there's a diaphragm, much like the altimeter's wafers, directly connected to the static line. Pressure inside the diaphragm changes instantly with altitude changes.
Okay. But what's different?
The difference is how the case surrounding the diaphragm gets its static pressure. The case is also connected to the static line, but through a very tiny restricted opening called a calibrated leak.
A calibrated leak. Sounds like a problem.
No, it's intentional. It means the pressure inside the case changes much more slowly than the pressure inside the diaphragm when you climb or descend.
Creating a pressure difference between the inside and outside of the diaphragm.
Exactly. During a climb, pressure inside the diaphragm drops instantly, while the case pressure lags behind, remaining higher for a moment. This pressure difference makes the diaphragm contract, moving the needle to show a climb.
And the opposite happens in a descent.
Correct. Diaphragm pressure increases instantly, case pressure lags, stays lower, diaphragm expands, needle shows a descent. Once you establish a steady rate of climb or descent, the pressure difference stabilizes, and the VSI shows that rate.
The handbook mentions trend versus rate information. What's that?
The initial movement of the needle, the very first indication that you're starting to climb or descend, that's the trend. It tells you the direction of the vertical speed change almost immediately.
Okay.
The rate information is the stabilized reading you get after a few seconds, showing your actual steady feet per minute climb or descent.
And there's a delay in getting that steady rate reading, lag.
That's the term. It takes a few seconds for the case pressure to catch up through that calibrated leak, so pilots need to anticipate this lag, especially when trying to level off precisely at an altitude. Rough flying or turbulence can make the lag worse.
And some planes have an IVSI, instantaneous VSI.
Yes, some more advanced setups use an IVSI. It uses accelerometers, little devices that sense vertical acceleration to help compensate for that lag and give a much quicker, more instantaneous reading of vertical speed changes. Pretty neat.
What's the VSI pre-flight check?
Simple one. On the ground, before taxi, it should read 0 or very close to it. If it's slightly off, just mentally note that as your 0 for the flight. Then during takeoff, watch that it correctly indicates a positive climb.
Okay, let's circle back to the airspeed indicator now. We know the basics, but let's get into the nitty-gritty. It's fundamental.
Absolutely foundational.
Yeah.
As we said, it's a differential pressure gauge. It measures the difference between that total pressure from the pitot tube.
Dynamic plus static.
Right. And just the static pressure from the static port.
And inside, the total pressure goes into the diaphragm. Static pressure surrounds it in the case.
You got it. The difference, which is the dynamic pressure, makes the diaphragm flex. And that movement is mechanically linked to the needle, showing your airspeed.
Okay, and just like altitude, there are different types of airspeed. Indicated, calibrated, true, and ground speed. Run us through those again.
Sure. Indicated airspeed, IAS. Raw reading right off the dial. Uncorrected for instrument or installation errors or air density changes. But crucially, it's the speed used in the POH for performance figures like stall speeds, flak speeds, etc. Those speeds correspond to specific aerodynamic pressures, which IAS represents well, regardless of altitude.
Okay, so V speeds are usually IAS.
Generally, yes. Calibrated airspeed, CAS. This is IAS corrected for those instrument and installation position errors. Errors are usually largest at slow speeds. The POH often has a chart to convert IAS to CS.
Getting more accurate.
Yep. True airspeed, TAS. Now, we correct CAS for altitude and non-standard temperature. Remember, air gets thinner as you go higher. To get the same indicated airspeed, same dynamic pressure, you have to actually move faster through that thinner air.
So TAS is always higher than CAS at altitude.
Generally, yes, unless it's extremely cold. TAS increases by about 2% per 1,000 feet of altitude above sea level compared to CAS. You calculate it precisely with a flight computer or use that rule of thumb. TAS is what you use for flight planning, how fast you're actually moving through the air mass.
And finally, ground speed.
Ground speed, GS. That's your actual speed over the ground. It's simply your true airspeed adjusted for wind. Headwind slows you down, tailwind speeds you up relative to the ground. GPS often shows ground speed directly.
Makes sense. Now, those colored arcs on the ASI dial, they look important.
They are. Standard markings for most light aircraft. The white arc, flap operating range. Lower end is VSO stall speed and landing configuration, gear, and flaps down. Upper end is VFE maximum flap extension speed. Use flaps only within this range.
Okay, flaps, white arc.
Green arc, normal operating range. Lower end is VS1 stall speed and clean configuration, flaps and gear up. Upper end is VNO maximum structural cruising speed. Don't exceed VNO unless the air is smooth, and even then, be careful.
Green is normal cruise.
Yellow arc. Caution range. Only fly here in smooth air and with caution. Turbulence in this range could overstress the aircraft.
Yellow or caution.
And the red line. VNE. Never exceed speed. Self-explanatory. Exceeding this speed risks structural failure, period.
Got it. White, green, yellow, red line. But there are other important speeds not marked directly on the dial, found in the POH or on placards.
Correct. Several critical ones. VA, design maneuvering speed. Max speed for abrupt control inputs or flight in turbulence. Importantly, VA decreases as aircraft weight decreases. Below VA, the plane should stall before braking. Above VA, you could brake something before it stalls.
Crucial one for turbulence or maneuvers.
Absolutely. Then for retractable gear planes. VLO, landing gear operating speed, max speed to extend or retract the gear. And VLE, landing gear extended speed, max speed to fly with the gear down.
Gear speeds, VLO and VLE.
Then climb speeds. VX, best angle of climb, gives the greatest altitude gain for distance traveled. Good for clearing obstacles. VY, best rate of climb, gives greatest altitude gain per unit of time, gets you higher faster.
VX for angle, VY for rate.
Right. And for twins, VYSC, best rate of climb, single engine, often marked with a blue line, best climb performance you can get with one engine out. And VMC, minimum control speed, the minimum speed you can maintain directional control with one engine out at takeoff power. Very critical speed for twins.
Blue line and VMC for twins. Okay. Pre-flight check for the ASI.
Should read 0 on the ground in calm winds, maybe a tiny bit higher if facing a strong wind. Then, during takeoff roll, just confirm it comes alive and increases smoothly.
All right. Now, blockages. We talked about the static system. What happens to the ASI if the pitot system gets blocked?
Okay, 2 scenarios. Scenario 1, pitot tube opening blocked, but drain hole is clear. Ram air can't get in. Pressure inside the pitot line drops down to ambient static pressure via the drain hole.
So pitot pressure equals static pressure.
Right. And since the ASI measures the difference between pitot and static, if they're equal, the difference is 0. ASI reads 0 airspeed.
Okay, blocked opening, clear drain equals 0 airspeed.
Scenario 2. Both pitot opening A and D drain hole blocked. Now you've trapped whatever pressure was in the pitot line when the blockage occurred.
So the pitot pressure side of the ASI is now fixed.
Essentially, yes. The ASI becomes an altimeter, almost. It won't react to airspeed changes anymore. But as you climb, the static pressure, in the case, decreases. Compared to the trapped higher pressure in the pitot line, this difference makes the ASI indicate higher airspeed.
So climbing with a fully blocked pitot makes the ASI read faster?
Correct. And descending makes it read slower as static pressure increases against the trapped pitot pressure. It acts like a reversed altimeter.
Wow, that's confusing and dangerous.
Very. That's why pitot heat is so important if you're flying in potential icing conditions. Use it before you get ice.
Good advice. And just to recap the blocked static system effect on the ASI.
Blocked static port, pitot tube clear. ASI still works, but inaccurately. It's now comparing good ram air pressure to a trapped, incorrect static pressure. If you climb above the altitude where the blockage occurred, the trapped static pressure is higher than ambient, so the ASI reads lower than actual airspeed.
Opposite of the blocked pitot effect during a climb?
Exactly. If you descend below the blockage altitude, trapped static is lower than ambient, so ASI reads higher than actual. And remember, blocked static also freezes the altimeter and zeroes out the VSI. Using the alternate static source helps, but check the POH for corrections.
Okay, that covers the pitot-static gremlins thoroughly. Let's shift to the modern cockpit. Electronic flight displays, EFDs, class cockpits.
Right, the PFDs, primary flight displays, and MFDs, multifunction displays. A big leap from the old steam gauges.
What are the main advantages?
Generally, better reliability, fewer moving parts, often lower long-term cost, and much less panel clutter. You can integrate the traditional 6-pack of instruments, plus engine data, navigation info, all onto 1 or 2 screens.
So how are those familiar instruments represented on, say, a PFD? Let's start with airspeed.
Airspeed is usually a vertical tape on the left side. Numbers increase going down the tape. Counterintuitive at first, maybe. Your current IAS is shown by a pointer or in a box. TAS is often displayed digitally at the bottom. You'll see bugs for V-speeds and the familiar color-coded ranges along the tape. The number might turn red if you exceed VNE.
And the attitude indicator.
That's usually the dominant feature in the center. A large artificial horizon display, much easier to interpret, especially in partial panel situations. It gets data from the AHRS, the attitude heading and reference system.
Altimeter.
Typically a vertical tape on the right side. Numbers increase going up the tape. Current altitude is in a digital box, often shows 20-foot increments.
ESI.
Usually right next to the altimeter tape. Can be an ORCID scale or another vertical tape. Often has a digital readout and a selectable vertical speed bug too. Below the attitude indicator, commonly presented as part of an HSI horizontal situation indicator. Gives you heading plus navigation info overlaid. Gets data from a magnetometer via the AHRS.
Turn indicator.
Often a little trapezoid or sliding bar under the roll pointer, the little triangle at the top of the attitude indicator, shows your rate of turn.
What about engine gauges, like the tachometer?
Usually on the MFD, the multifunction display, But if one display fails, critical engine info like RPM will typically pop up automatically on the remaining PFD screen. Backup modes are built in.
And the slip skid indicator, the ball.
It's there too. Usually a little horizontal line under the roll pointer moves left or right, just like the ball in a traditional turn coordinator. Step on the line, just like you'd step on the ball.
Turn rate indicator.
Often shown above the HSI compass rose. Tick marks for standard rate turn, half standard rate. Sometimes has a trend vector showing where your turn rate is heading in the next few seconds.
So very integrated. And these displays are software configurable.
That's a big plus. The look and feel, what information is prioritized, can often be adjusted via software updates or pilot preferences within limits, much more flexible than hardwired steam gauges.
You mentioned the ADC Air data computer. What's its job?
The ADC is the brain behind the pitot-static instruments in a glass cockpit. It takes the raw pressure inputs for the pitot tube and static port, plus temperature from an OAT probe. It does all the calculations to figure out IAS, TAS, altitude, vertical speed, OAT, density, altitude.
All the stuff we just talked about.
Exactly. Then it sends that digital data to the PFD displays and often to the autopilot as well. Usually a self-contained electronic box, relatively easy to replace if it fails.
And those trend vectors on the airspeed and altitude tapes, what are they showing?
Those are super useful. Usually magenta lines extending from your current airspeed and altitude bugs. They show a prediction, typically 6 seconds into the future, of where your speed and altitude will be if the current trend continues.
So they help you anticipate and make smoother corrections.
Precisely. They show the immediate effect of a pitch or power change. Makes it much easier to level off smoothly or capture a target airspeed without overshooting. Really helpful for precise instrument flying.
Very cool. Okay, let's move into the gyroscopic instruments. Different principles at play here.
Totally different. These rely on the physics of spinning objects' gyroscopes. The main ones are the turn coordinator, heading indicator, and attitude indicator. Understanding them means grasping, well, how gyros work, how they're powered, and how each instrument uses those principles.
So what is a gyroscope fundamentally?
It's basically a spinning wheel or rotor, mounted so it's free to rotate in different directions. The key things that make it work for instruments are having significant mass concentrated at the rim, spinning really fast, and having very low friction bearings.
And how they're mounted matters. Free versus restricted mounting.
Yes. A freely or universally mounted gyro, like one in gimbals, can maintain its orientation in space regardless of how the base moves. It has 3 axes of freedom. A restricted or semi-rigidly mounted gyro has one of its axes fixed relative to the instrument case, limiting its freedom. Which mounting is used depends on which gyro property the instrument needs.
And those 2 key properties are rigidity in space and precession.
Those are the magic principles. Rigidity in space. A spinning gyro wants to keep its axis pointed in the same direction in space. Think of a spinning top or a bicycle wheel. The faster it spins, the more stable it is, the more it resists being tilted.
Like it has inertia in its orientation.
Good way to put it. Precession. This is the interesting one. If you apply a force to try and tilt a spinning gyro, it doesn't tilt in the direction you push it. Instead, it tilts or turns at a point 90 degrees later in the direction of rotation.
A delayed reaction, sort of.
And at a right angle. This effect is what allows instruments like the turn coordinator to sensor rate of turn. The force of the turn causes the gyro to precess, and that precession moves the needle or symbol. Precession also causes small errors, like drift in the heading indicator, that pilots need to correct for.
How are these gyros powered? Needs energy to spin fast.
3 main ways: vacuum systems, pressure systems, or electricity. Many planes have a mix, often using different power sources for, say, the attitude indicator versus the turn coordinator, providing redundancy. If one system fails, you still have some gyroscopic information.
How do vacuum or pressure systems work?
They use air. An engine-driven pump creates suction, vacuum, or positive pressure. This airflow is directed through the instrument cases and hits little buckets or vanes on the rim of the gyro rotors, spinning them like tiny turbines.
Like a water wheel, but with air.
Exactly. There's a gauge in the cockpit to monitor the vacuum, or pressure usually needs to be in a specific range, like 4.5 to 5.5 inches of mercury for vacuum systems. Low pressure means the gyros spin too slowly and become unreliable. There are filters, relief valves. The whole system needs to be working right.
Okay, let's look at the turn indicators. Turn and slip and turn coordinator.
Right. These show the rate and direction of turn. They also provide backup bank information if the attitude indicator fails. And both have that little inclinometer, the ball and the curved tube, for checking coordination.
What's the difference between the 2 main types?
The older turn and slip indicator has its gyro spinning vertically, aligned fore and aft. It primarily senses yaw, the aircraft's rotation around its vertical axis. A simple needle shows the rate of turn. The turn coordinator has its gyro canted upward slightly. This canted mounting makes it sensitive to both roll and yaw.
So it reacts quicker when you initiate a bank.
Yes, it shows the rate of roll initially, then settles down to show the rate of turn once stabilized. Its display is usually a little miniature airplane that banks visually. Pilots use the turn coordinator to establish a standard route turn, 3 degrees per second, by aligning the miniature wings with index marks. Remember, though, it shows rate of turn, not bank angle.
And the inclinometer, the ball, that's all about coordination.
All about coordinated flight, using the right amount of rudder for the amount of bank. Ball-centered coordinated turn. Ball slips to the inside of the turn, not enough rudder, or too much bank. Ball skids to the outside, too much rudder, or not enough bank.
Step on the ball.
That's the correction. Apply rudder pressure on the side the ball's deflected towards to center it. It indicates side slip.
And the yaw string. Simple but effective.
Very simple. A piece of yarn taped to the windscreen, streams straight back in coordinated flight, deflects sideways if you're slipping or skidding, gives a direct visualization of the airflow over the nose.
Pre-flight checks for turn indicators.
Check the inclinometer fluid, make sure the ball moves freely. During taxi turns, confirm the turn coordinator needle or miniature plane moves in the correct direction and the ball moves to the opposite side of the turn.
Okay, now the attitude indicator, the AI, often the centerpiece instrument.
Definitely the primary reference for pitch and bank attitude. Shows a miniature airplane against an artificial horizon line, directly mimicking the aircraft's orientation relative to the real horizon. Gives you an immediate picture.
How does its gyro work? Rigidity in space again?
Yes, primarily rigidity in space. The gyro spins on a horizontal axis. The horizon bar is attached to the gyro mechanism. Because the gyro holds its orientation in space, as the aircraft pitches and rolls around the gyro, the fixed horizon bar appears to move up or down, or tilt, relative to the miniature airplane fixed to the instrument case.
So the gyro stays level, the plane moves around it.
That's the concept. There's usually a knob to adjust the little airplane symbol up or down slightly, just to match your viewpoint in level cruise flight. The bank angle is shown by a scale at the top, usually marked in degrees, 10, 20, 30, 60, 90.
Any limitations? Can they tumble?
Older ones could. They have pitch and bank limits, maybe 60 degrees pitch and 100 degrees bank. Exceed those limits, and the gyro could tumble, essentially get knocked off its axis, and give completely false readings until it's reset. Very bad in IMC. Modern AIs are often designed not to tumble or have much higher limits.
Good improvement. Let's do the heading indicator, or directional gyro, DG.
This one helps overcome the errors and instability of the magnetic compass. It provides a stable heading reference.
Based on rigidity in space, too.
Yes. This time, the gyro spins on a vertical axis. The compass card is attached to the gyro. The gyro holds its orientation in space, so the compass card remains stable, showing the correct heading as the aircraft yaws around it. Much easier to read than a swinging magnetic compass.
But it drifts. It needs resetting.
It does. Because of internal friction, the gyro precesses slightly over time, causing the heading reading to drift or creep. Also, because the Earth rotates underneath the gyro, which is holding its alignment in space, there's an apparent drift due to Earth's rotation about 15 degrees per hour.
So you have to periodically check it against the magnetic compass and reset it.
Exactly. Usually every 15 minutes or so, in straight and level unaccelerated flight, you adjust the HI to match the magnetic compass reading.
Unless you have a fancier system, like an HSI with slaving.
Right. More advanced systems, like many HSIs, are slaved to a remote magnetic sensor called a flux valve or magnetometer. This sensor continuously detects magnetic north and automatically corrects the heading indicator so no manual resetting is needed.
And the AHRS in glass cockpits, how does that fit in?
The AHRS, Attitude and Heading Reference System, replaces the mechanical gyros entirely. It uses solid-state sensors like lasers or MEMS accelerometers and rate sensors to determine attitude and heading. It gets heading data from a magnetometer. No moving parts to tumble, much more reliable and accurate. It feeds the attitude and heading displays on the PFD.
What about those flux gate compasses and remote indicating compasses?
Those are essentially the technologies that enable the slaved heading systems. The flux gate or flux valve is the magnetic sensor, usually mounted remotely, like in a wingtip, away from magnetic interference in the cockpit. It detects the Earth's magnetic field lines. The remote indicating compass system takes the signal from the flux valve and uses it to drive the display in the cockpit, like an HSI or RMI radio magnetic indicator, often incorporating a gyroscopic element for stability, but automatically correcting it to the magnetic heading. These systems provide much more accurate and stable magnetic heading information than a basic HI.
Can the basic HI tumble too?
Older, air-driven ones often could if pitch or bank limits, maybe 55 degrees, were exceeded. They'd need resetting with a caging knob. Newer electric ones often don't tumble. And again, low vacuum pressure is bad news for air-driven chair. His makes them slow and inaccurate.
HI, pre-flight check.
Listen for weird noises as it spins up. Check it indicates turns correctly during taxi. Note any excessive drift. Be aware vacuum might be low at idle.
Okay, last one in this group. Angle of attack, AOA indicators. Different focus here.
Very different. Not about attitude or direction, but about aerodynamics, how the wing is meeting the oncoming air. It directly measures or computes the angle between the wing chord line and the relative wind.
Why is that useful? Isn't airspeed enough to avoid stalls?
Airspeed isn't the whole story for stalls. Stall speed changes with weight, bank angle, G-loading, configuration. But an aircraft always stalls at the same critical AOA for a given configuration.
Ah, so AOA is a more direct measure of stall margin.
Exactly. AOA indicators provide a visual representation of your current AOA relative to the critical stall AOA. Gives you immediate awareness of how close you are to stalling, regardless of your airspeed or weight. Great for energy management, especially during takeoff, approach, and maneuvering.
Makes sense. Okay. Final system. The magnetic compass. The old reliable.
The oldest direction finder, and still required. It works because the Earth itself is a giant magnet. The compass has small magnetized needles that align themselves with the Earth's magnetic field lines.
Describe the basic construction.
It's pretty simple. You have magnets attached to a float assembly, which sits on a pivot inside a sealed bowl filled with fluid like kerosene to dampen oscillations. A compass card marked with directions is attached to the float. The magnets align with magnetic north, and you read your heading off the card against a fixed vertical line called the lubber line. Remember, the card stays mostly still, pointing north, and the airplane rotates around it.
But it's prone to errors. Let's cover those. First, variation.
Variation, or declination, is the difference between true north, geographic pole, and magnetic north, where the compass points. They aren't in the same place. Charts are based on true north. Isogonic lines on charts show lines of equal variation. You have to add or subtract variation, depending if it's east or west, to convert between true and magnetic course headings. East is least subtract. West is best. Add. Going from true to magnetic is one way to remember.
Okay, that's geographical. Then deviation.
Deviation is caused by the aircraft's own magnetic fields, radios, electrical wiring, metal parts. This error is specific to the individual aircraft and changes depending on which way the aircraft is heading.
How do you deal with deviation?
An aircraft mechanic swings the compass. They taxi the plane onto a marked compass, rows on the ground, note the compass reading on various headings, and adjust small compensating magnets inside the compass to minimize the error. Then they create a compass correction card, posted near the compass, showing the remaining deviation on different headings. The pilot uses this card to correct magnetic heading to get compass heading.
So the sequence is true course, apply variation to get magnetic course, apply deviation to get compass course to actually steer.
Correct. TVMDC, true, variation, magnetic deviation, compass, working down or up.
Now, dip errors. Earth's magnetic field isn't horizontal.
Not usually. It dips downwards towards the magnetic poles. The compass wants to align with these dipping lines, but it's weighted to stay mostly horizontal. This causes errors during turns and acceleration-deceleration.
Northerly and southerly turning errors.
Okay, in the northern hemisphere. Turning from or through north, the compass initially leads the turn, then lags. So when rolling out on a northerly heading, you need to stop the turn before the compass reads north, undershoot. Turning from or through south, the compass lags behind the turn. So when rolling out on a southerly heading, you need to let the compass swing past south before stopping the turn, overshoot. The amount of lid lag depends on latitude. UNOS, undershoot north, overshoot south.
Got it. An acceleration error, the NDS thing.
On east or west headings, acceleration makes the compass indicate a turn towards north. Deceleration makes it indicate a turn towards south, ANDS, caused by the compass card tilting due to inertia and magnetic dip. No error on north-south headings.
An oscillation error.
That's just the compass swinging around due to turbulence and all these combined errors. Makes it hard to read accurately sometimes. Use the average reading when setting your HI.
What's the vertical card compass?
It's designed to be easier to read. Looks more like a heading indicator with a fixed airplane symbol and a rotating vertical dial showing the heading directly behind it. Reduces some of the reverse sensing confusion of a standard compass. Still subject to dip errors, though.
Okay. Last instrument mention, The outside air temperature OAT gauge.
Pretty straightforward, usually a bimetallic thermometer probe sticking out into the airflow. Displays the OAT in Celsius or Fahrenheit or both. Important for performance calculations, icing awareness, and checking temperature trends with altitude.
Phew. We've covered a lot of ground, or maybe airspace. A really comprehensive deep dive into flight instruments.
Absolutely. From basic pressure principles in the pitot-static system through gyroscopic magic to the quirks of the magnetic compass, understanding these is just fundamental to flying safely.
We hit the pitot-static instruments, ASI, altimeter, VSI, talked about EFDs, the glass cockpit revolution, dived into the gyros, attitude, heading, turn indicators, even AOA, and finished with the compass systems.
And the big takeaway for you listening is really internalizing how these things work, what makes them lie sometimes, the errors, the blockages, and how to interpret them correctly. That knowledge is key to making good decisions, especially when things get busy or visibility drops.
Definitely. So here's a final thought to leave you with. As these flight instruments get more and more sophisticated, more automated, more integrated in glass cockpits, what are the new challenges? Could pilots, maybe, face difficulties in keeping those basic steam gauge instrument skills sharp? Or perhaps struggle to recognize really subtle electronic malfunctions that aren't as obvious as a needle just falling off? Something to think about as aviation technology keeps advancing. Thanks for joining us on this deep dive.